Yes.
Yes.
Let's share the screen. Okay, so facility management, that's another promising use of a VR and also AR, especially AR, since this is facility management. So I'm going to play a quick video by Bentley, and they had this project several years ago that how HoloLens AR goggle can help uh, identifying the issues with the pipeline system and also fix the problem. You will see multiple functions in this project.
When you have located the affected system, say, acknowledge alarm.
Acknowledge alarm.
To leave alarm mode, say, clear alarm.
Okay, something's wrong here.
What
What's
do
the
you see? The
problem?
blue, the
Display
purple dot here
PMID.
is the eye tracking, the gaze focus.
Well, we have a heat exchanger here. Okay. Describe alarm.
Pressure at instrument PIT 5003 is below 2 psi threshold. Current pressure is 1.5 psi.
Okay, PIT 5003, that's the one. Locate item. Where is it? Okay, that's the one. Yeah, the pressure is very low. Are there some readings for this? Display readings history. Move. Okay. There was a maintenance on Wednesday, July 13th. Oh, there was also here and here. And just before that, the pressure was very low. And after that, the pressure gets back to normal. But there are some very high peaks of pressure. And after the peaks, the pressure seems to decrease. That's weird. Hide. Well, are there some video reports for those maintenance? Display maintenance history.
There is a video clip for the third entry.
Move. Okay, there's a video.
Okay, so what you're seeing here is more than a video. This is actually a 3D model of a person, which means if you walk around and turn around, you actually see a 3D virtual person standing in front of you. And this was also recorded by this HoloLens goggle. This goggle has something called a depth camera. Guys, remember we talk about scanning, LiDAR scanning, depth camera scanning, and the photogrammetry. This is the second method. So it's a camera that can tell you the depth information and create a point cloud model of a person. Okay, so this is the application of that in AR.
Okay, hi, I'm Ben O'Connor, and it's October 23rd, 2016 in the afternoon. Actually, it's 1:18 p.m. Today, the pressure indicating transmitter 5003 stopped working properly. Measured pressure was way too low, so I replaced it. But we did the same thing last month and back in July, so that means we replaced it 3 times in 4 months. That's way too much for these type of device because they usually last more than a year. It indicates there's probably something is wrong with the system, but we would need further investigation to confirm that. See my report for additional details.
Okay. Hide. So the problem keeps repeating. We'll have to do something about it. Clear alarm. Okay, since this is a heat exchanger, the instrument indicates the differential pressure between this pipe and this pipe. And why the instrument is broken, maybe because the differential pressure gets too high between those two pipes. So a solution to this could be to add a bypass between those two pipes. Well, let's do that. Okay, those are the pipes in question. Okay, add bypass.
When you have found a suitable configuration, say, Accept bypass to save your design.
Okay, I need to find a good configuration.
And guys, here you see why VR AR is more than 2D and is better than 2D, because you have this bypass design in that schematic design. It's not enough. You still want to see if it has any potential spatial conflicts, if you do you have enough clearance for maintainability, for accessibility. So that's why VR AR plays a much better role. Oops, my goodness.
Sure is very low. Are there some readings
Configuration, say,
to find a good configuration? Okay, this is the bypass, but right now it is red, indicating that it's colliding with this pipe. Move. If I move it here, well, that's not better, since it is occluding the instrument. Move. If I pull it here, well, this is in the way. If I push it here, I think this could be good. Yeah, that's interesting. Okay, I think it will be that. Accept bypass.
your design has been saved. Returning to free mode.
Okay, so we have to plan a maintenance for the modifications, and the problem should be solved.
All right, here it is. So let me skip that. Okay, so we talk about the VR AR applications for design, for construction, for maintenance, for pretty much all the phases. And you also probably can see the obvious benefits of VR AR. But here's a in-depth question: are they always better? Think about that. Like I mentioned earlier, the evolution of our industry is actually the evolution of information. So we are moving from 2D drawings, specs, text information, to 3D models, to VR. So guys, do you think VR will benefit our industry? Is that a guaranteed? Anybody? Nobody? Okay, so actually this is the question that people are asking. Looks like VR looks as a better solution. And so they basically studied and they did a survey by giving construction workers VR and by giving them the traditional like a 2D drawings or other kind of information technology and to check their performance. Guys, what happened? We see the conflict findings. Some literature shows that yes, the use of VR AR can improve the performance of construction. But some people found the upside. They see by using VR AR, they actually observed no change or even worse performance in construction. And what's more interesting is they actually have the same explanation, more information. So they say, for those who supported that VR can benefit our industry, they say it's all because VR and AR can provide additional information. Think about that. Instead of staring at a 2D drawing, by looking like VR, you actually have information about a 3D spatial coordination, and you can look around, walk around. Yeah, that's additional information, additional spatial information. So that must help with the understanding of the project. But also, people found, that VR will hurt the performance. They also argue it's all because VR AR provided more information. So more information means additional burden for the construction workers to process. So that's very interesting. Different observations, same explanation. Then it made us to investigate. That's my research team to investigate what actually happened. So what do? We measure cognitive load. So we think the key is what happens in your brain. Additional information from the function perspective, yes, they should benefit a better understanding. But also we agree that it might burden your information processing process, may burden your brain. So we really want to see what's going on in the brain. So we use this device. This is a neural imaging device called FNIRS. So this one, all the red dots will send infrared light into our brain, and the blue dots will track how much infrared light is absorbed by certain areas of your brain. Because oxygen and the carbon dioxide are absorbing different wavelengths of infrared lights in different way. So by checking how much is losing, we know how much oxygen and how much carbon dioxide in this area. So we can somehow tell if your brain is more active in this area, if your brain is more active in that area. And since our brain has different functions, let me show you this quickly. So since our brain, different areas of our brain are responsible for different functions, by checking the oxygen and carbon dioxide, we can somehow tell if we are overloaded by certain things. So let me stop sharing my screen for a moment. You see this model of my, not my brain, a model of brain. This is the front of brain, this is the back of the brain, okay? And the front end is called the prefrontal cortex, or PFC. This one is more responsible for memory, for planning. If you want to do a complex task with certain sequence of activities, so this one is planning it out. And the two sides of brain, here and here, these two sides of the brain is called the premotor cortex and the motor cortex. This one is more responsible for coordinate your actions, like if you're swimming, if you're riding a bike, those two parts will be more activated. And the back of our brain, the back side of our brain is responsible for image processing. So actually your eyeballs receive the signal, and all the signal, the visual signal will be going all the way to the back of your brain to process. And also in the middle of your brain, there's a area called a hippocampus. The hippocampus is the one for spatial memory. So if you check the taxi drivers in London, their hippocampus is about 15% larger than other people, because they often use their brain to remember, the space. So this is for the spatial memory. And so by checking the brain activity, the oxygen level consumption, the carbon dioxide consumption, we can somehow tell, if this person is more engaged in memorizing the information, or if this person is more engaged in all the actions, things like that. Okay. And also we check their pupil size. As you can see, this is the infrared lights built in this VR goggle. It shoots infrared lights into your eyeball. And we also have a small camera to check the change of your pupil size. And if you are thinking too much, if you are engaged in a task, your pupil will become larger. And also we check your heartbeat. The heartbeat can also tell if a person is thinking too much. Okay,
Professor?
so this, yeah, go ahead.
So you consider the cognitive part as the parameter for this particular research you did, right?
It's the measure we are measuring, yes.
But it can vary from person to person. So how dependable could it be in terms of the research?
Baseline. We check the baseline for each person, and we just check the pure marginal increase of that.
Okay.
Yeah. So this is the video of showing how this program and this device is checking. You see, this is the pupillary size change, and also it checks the eye focus, like where you are looking at, and also the blinks of your eyeball. And also we found the pupil size can also be affected by light, right? So if it's too bright, your pupil will shrink, we know that. But we want to focus on the pupillary change purely driven by the cognitive load. So how can we do it? We have this innovative way. We calculate the RGB value of each pixel, and the RGB value can be translated into the luminance. And then we have this mathematical function to remove the light response from your pupil size data. So the residual would be the pupil size change purely driven by our cognitive load. And why we need this complex mathematical function? Because we also have this latency driven by the light change. For example, if I turn off the light in this room, my pupil will become larger. But if you take from 500 milliseconds to 2 seconds to change that size, and it's different from person to person. So, and also when you are drinking coffee too much, when you are lack of sleep, or when you are in different mood, that latency will also change to you. So we have to use a mathematical method to tell, when the light condition changes and when we see a significant change of your light response. And we basically move the two curves, find out the matching point, and remove the light response from the data. Okay, so it's not an easy task, but we did that. And then we did the experiment. So we gave people 2D drawing, 3D model, VR. We track their focus, eye focus. We track their motion. We track their brain activity, and we want to see when they are using different information, how that is changing their performance. Like for example, this is eye tracking. As you can see, it basically tracks we are looking at the 2D drawing, and also it tracks we are looking at the 3D model, like a Revit model. Let me stop this one. See, this one also tracks, the 3D trajectory of your gaze focus. Okay, so this is some example of that. Like this one shows we gave people the specifications and the isometric drawing for pipe maintenance task. This one shows actually different people had a very different focus pattern. Okay, and this one shows the 3D trajectory of your gaze focus. It shows the lines that you are looking at the space and you are plotting a virtual line in the space. So we actually documented that so we can study how fast you're moving your eyeball and the pattern of the line, the focus area of the line. And this one shows the pupil size. So X is the frames, 90 frames per second, and Y is the size of your pupil. Unfortunately, we didn't change the unit measures. This is meter. So which means this is a 3.5 millimeter, 3 millimeter, 4 millimeter. And this one shows the change that all the sudden drops were blinks. Like if you blink more often, if you blink less often, that also shows if you're thinking too much, if you're overloaded or not. So that's all the data, to give example. And of course, we collect your brain activity. So this one shows, the oxygen consumption in your brain. Red means you are consuming more oxygen, and blue shows more carbon dioxide. You guys see it's flashing, it's beeping, right? So why it's beeping? Anybody?
Does it shows the active part of your brain or something?
This is showing the real-time activation activities of in your brain, but why it's flashing like this? Why it's beeping like this? It's heartbeat. Because this is oxygen and carbon dioxide, your heart is beeping. You see that in your brain data. So actually, we need to remove the heartbeat to focus on the pure change driven by the cognitive load. Make sense? Okay, so then we actually did an experiment, like we give people 2D drawing, textual instruction, 3D model, VR, and we ask them to finish this pipe maintenance task while we're monitoring all their personal data.
All right. So.
And you can see, people have different performance. Like somebody performed that really fast, somebody it took them longer, and they have to think longer. Okay, so here's the result. First we check, how different formats information affect your performance, in terms of the accuracy and the response. We found yes, 3D and VR benefited your performance. In terms of accuracy, this 3D and VR group, the accuracy were better than 2D drawing, and 2D complex means a lot of wording, a lot of textual instruction as well. So yes, they were better, and they were faster in terms of operation time. Then we check the cognitive load. So our original thought is, since 3D and VR could lead to better performance, so they must have reduced your cognitive load. That's reasonable, right? That's natural. But guess what? This one shows their cognitive load and group. In fact, it shows that 3D and VR actually led to higher cognitive load. So then that's an interesting question. So you were actually feeling more difficult of using 3D and VR to get your performance, but your final performance were better. So what happened here? Then we figured out the information actually plays two roles. One is, when you are trying to memorize the information, you are digesting the information, like you're holding a 2D drawing, you try to understand what's going on here. That's called information encoding. You are writing information into your brain. But when you are working, you are actually trying to read information. It's kind of like reading the information from your brain. So we start to think, maybe 3D VR can benefit your performance because in the operation phase, when you are trying to retrieve information, we are trying to read information from your brain, it made it easier. And the answer is correct. So this is during review, 3D and VR increased the cognitive load, but during performance, they actually decreased the cognitive load. So we start to think this. This is the input process operation input process output process. So we gave information in 2D, in 3D, in VR to you, to a person. Then you need to write them into your brain, hold them for a while, and when you have to use them, you need to read them. 3D and VR actually made the reading, the writing part, the encoding part, more difficult. But it made this one, the reading part, easier. And there's a conversion ratio, the cognitive load in this phase divided by the cognitive load in that phase. We checked the ratio for each group and we found, yes, 3D VR shows a more efficient way of converting information from encoding to recalling that information. What does that mean, guys? That means 3D and VR will make the learning, will make the training, will make the reading more difficult. But whenever after that, when you put the construction workers to work, they feel it's much easier. That actually answers why literature tend to give conflict results. It made the learning difficult, but it make the work easier. You guys understand that? So when you give a 3D model VR to a person, yes, they have to digest more information. There's an information overloading, there's a cognitive overloading. But because of that, because the VR simulates a world, simulates an environment that is so similar to the actual, work environment, when you are working, you feel so familiar and you feel more comfortable of doing things. And that also answers why, whenever we are talking to general contractors, construction companies, say, hey, why don't you use VR to instruct your construction workers their jobs, to train them? They say, no. They always say it's more difficult. Yes, we agree. It's more difficult for them to use it to remember the information, but it's much easier for them to use that. And what is more important, guys? Which scenario we need? We want to move the difficult to the beginning. So when they're doing their work, it's easier. And further, we discovered there's something called cognitive budgeting theory. That's some theory we proposed. The amount of brain energy, the amount of a cognitive process you need for finishing the entire process here, from encoding the information to recalling information, is actually the same. 3D VR don't change anything. They are only moving the load to the front end. Make sense? So now think about the argument we have in the current literature. Somebody say 3D VR can reduce the load. Somebody say no, 3D VR can increase the load. The answer is no. 3D VR doesn't change load at all. It's just about moving the load, from the back end to the front end. So it's actually a higher level view of what's going on here. And we actually doing more. We found the picture, the story is even more complex. Like depending on the type of information, phonological information such as words, numbers, symbols, visual spatial information such as colors, lines, they're actually triggering very different process in our brain and triggering different areas in our brain. So my research team is actually researching how VR AR can manipulate this process and make better use of your brain. So that's actually a quick view of VR AR. So to recap quickly, VR AR is becoming more and more popular in our industry, because we figured out that a lot of problems in our industry is the lack of communication. And VR AR is a natural way, intuitive way to communicate complex information. So that's why we start to see a lot of applications in design, in construction, and also in facility management, okay? But when you are talking about the sense of VR AR, of improving or affecting your performance, this actually is something about cognitive process. So VR AR doesn't change your cognitive load at all. It's just reallocating the load to the front end, which is more desired scenario in our operation. Okay, so that would conclude our talk. And any question, any comments? Go ahead.
Sorry, go ahead, Alvaro.
Oh yeah, I just wanted to share. I saw an article in the MIT Technology Review magazine in the past. I think it was last month. It's kind of related to this because there's like a startup in Israel that it's putting cameras in workers' helmets, and basically it's running an artificial intelligence software, and it's kind of like spotting in real time like mistakes and errors in the construction and kind of like throwing alerts for engineers or like managers. Also, this is happening in this zone. So it's kind of like a mixture of, it's not virtual reality or anything like that, but it's kind of like a mix, like throwing artificial intelligence, because it's like comparing it to the digital model. So I just wanted to share that. I thought it was really interesting.
Yeah, thank you for sharing. In general, this is about a human-computer interaction. I guess the true benefits of a VR AR is it provides another way, intuitive way for us to interact with automation system. Imagine, when we start to have a computer, the only way for us to interact with it is to code the lines of data, right? So we have to use the keyboard to put the lines of data. Then we have this invention, Morse. It's easier for us to interact with computer. Then we have the voice control. Then we have the 3D models. And nowadays we have the VR. It's just yet another way to interact with machine. And the one you mentioned that reported by MIT Tech Review, I think it's the same thing. It's just a more intuitive way of interacting with machine. And yes, that will be coming. Thank you for sharing.
Yep.
Go ahead. Okay.
Yep.
Yeah, go ahead. Sorry.
Is there any difference between AR and VR? I feel like they are the same.
No, like I mentioned earlier, VR, you cannot see the real world outside you. But AR, yes, you can see the real world outside you. Got my point?
Oh, okay.
Yeah. So like when you put on a VR goggle, it's always dangerous to walk around because you cannot see the real world. But AR, you can definitely walk around.
Oh, okay, I see now.
Yeah. Any other question, guys? All right. So if no question, guys, please do me a favor. I understand that you are receiving the link for teaching evaluation. I always want to see your comments and feedback. So please take, I think, 5 minutes to respond to that. And work with our team on the 5D and the final presentation. So next week would be the reading week, there's no classes. And see you guys on the 17th. I'm going to send an email to confirm that. All right. So see you guys in 2 weeks.
Thank you.
Thank you.
Bye.
Bye.